Hello, good morning, everyone, and welcome to the ADS-CFT at 20 meeting and to ICTS for those of you who are here for the first time. I'm really delighted that you could make it for this meeting, and many of you come from afar, and we hope to have 2 weeks of very stimulating interactions and go on to the ADS-CFT at 20 and beyond part. So hopefully there will be a lot of that. And at ICTS, I will tomorrow, before Juan's Chandrasekhar lectures, I'll give a small overview of what ICTS is about. But today I will spare you that. I just wanted to say that in our campus, feel free to use all the facilities. There is a gym, and of course, if the weather is good, you can also use the swimming pool and so on. So all the visitors are very welcome to enjoy the campus facilities. And there are also some bikes, and you can borrow them at the gate and go around, but just be a little bit aware of your surroundings while you're doing that. But there is a lot of countryside around to explore. So with that, let me hand it over to Loga to start the proceedings.
Okay. Thanks, Rajesh. So we will start with Mukund telling us about entropy from superspace inflow.
Thanks, everyone. It's great to be back. I was here not so long ago, and it's always fun to see various friends. So in thinking about what to talk, I took to heart the title of the conference, and roughly speaking, the sort of time span over which ADS-CFT has been in public consciousness is also my career span. The paper by Juan came out about a month or two after I started grad school. And so I want to sort of go back to certain things that, to some extent, inspired indirectly in the context of what I'm going to talk about, the ADS-CFT correspondence, namely black holes, and try to tell you a story of trying to understand parts of black hole dynamics in terms of fluid dynamics and how that helps us understand entropy from a very different perspective than what we are conventionally used to. Okay? The punchline is going to be the subtext of the title, which is entropy is in the context that I'm going to talk about, Noetherian, and I'm going to pose a much more general question for the beyond part, which is how much more generally is that statement true? So this is something, the main stuff is stuff I've been doing with my former student Felix, who is now at Vancouver, and Loga, who you all know. And I'm going to apologize to those of you who've heard me or Loga talk about this over the years. This is something that we've been doing for 3 or 4 years. And then the other people, other groups who've sort of pursued similar agenda. So there's a group of former MIT students, Crossley Glorioso, Harvard student Gao, and Hong Liu from MIT. And there's a group of people from UCSF, SF State, Haifa, and Brussels, Jensen, Yarom, Pinzani Fokiwa, and Matke. And so I'll mention connections and relations, if any, as we go along. Okay, so let me start with something that's old. It's older than ADS-CFT, but it will set the context for what I want to say. Okay, but before I do that, let me also give you a summary of what the 3 statements, summary of the talk, which I'll flash back again at the end, but to keep in mind where we are going. So first statement I'm going to make is that entropy is obtained from a Noether procedure in equilibrium. I'll demonstrate this explicitly. This is easy to understand, and for reasons I will explain in 5 minutes, this ought to have been true from the get-go in ADS-CFT, and now we know it is true. A slightly more surprising statement is that entropy also happens to be Noetherian in systems which are slightly away from equilibrium, but away from equilibrium arbitrarily in amplitude, but slowly varying in space and time, fluctuations that vary slowly in space and time. Now, if entropy is Noetherian procedure gives you something that's conserved, it doesn't give you a non-conserved current. So you may wonder, how is it that entropy can at the same time be a Noether current and be produced in physical processes? And I'm going to suggest a mechanism by which this happens. And to do that, I'll have to introduce lots of machinery. But roughly speaking, the punchline is going to be that the conservation of entropy happens because there's a topological sector that produces entropy and passes it on to physical space. Okay? So the equation won't make any sense now, but hopefully by the end of the talk, you'll see why this statement is true. To give you an anchor point for intuition, I want to draw an analogy with something which sort of explains the title of the talk. The anchor point is how so classical systems have symmetries, and these symmetries can be used to construct currents if the symmetries are continuous by a Noether procedure. But these symmetries don't have to stay in the quantum theory, they can be anomalies. Now, what that usually means, and as you know in the case of the ABJ anomaly, the current is not conserved, but the right-hand side of the current has some explicit source terms, like E dot B. And you might ask, how did that come about? How would you construct some theory which allows you to write down a current that has an effective action that has a non-conserved current while keeping the symmetries manifest? There's a trick to do this, and this trick goes back to Kellner and Harvey. But it's a trick that's well known in simpler systems like quantum Hall systems, whereby you take your system that has an anomalous symmetry and you couple it to a topological theory. In this case, if you think of a Hall system, the Hall system lives inside the cylinder. It's a 2+1 system. It's a topological Chern-Simons theory. But the boundary of this Hall system has chiral states, so some chiral Vesu-Minowitten model. And the current is the chiral current of the Vesu-Minowitten model. That current suffers from an anomaly. It's not conserved by itself because it's chiral, it's unidirectional. But the combined current contribution from the variation of this action of the Chern-Simons theory plus the boundary Vesu-Minowitten model is conserved. And this mechanism, due to Kellner and Harvey, is called the anomaly inflow mechanism. In some sense, anomaly flows in from the topological sector into the boundary. So the story is going to be quite analogous for entropy, but instead of having a topological field theory that produces entropy, we are going to have entropy come in from topological directions in space-time. So to superspace directions in space-time. Very good. So let me now go back and remind you of some facts that some of you know very well and explain why entropy should have been Noetherian in the first place. Okay? Now, there's a context where we know it's true, and I'll use that context as a springboard to inspire myself of why this must be true more generally. So let's talk about thermodynamic entropy to begin with. So in the macrocanonical picture, there's not much to say, you just count. But in the canonical picture, it's the von Neumann entropy for some Gibbs state, and for simplicity, I'll only talk about the thermal Gibbs state. I won't turn on any chemical potentials or charges. We can run the argument for those cases, but equations will get more messy. So let's just stick to the thermal Gibbs state. Now, all of you know this, that it's one way to think of this Gibbs state is either as a density matrix acting on your quantum Hilbert space, or you can think of it as a state in a double Hilbert space, which is a thermophile double state where you construct the state by pairing two copies of your system. In some sense, you take your system and its CPT conjugate, you flip the CPT conjugates around to make them states, and then you write down this thermophile double state by pairing states appropriately by appropriate Boltzmann factors. In the thermophile double context, the thermodynamic entropy of this Gibbs density matrix is nothing but the von Neumann entanglement entropy of the thermophile double state, which is not a pure, but it's a mixed state to begin with. Now, let's talk about how this is realized in gravity, where this seems to be the most natural way to think about black holes. One way to do this is to think about the Euclidean construction of this thermophile double state. You can prepare this by taking the Euclidean path integral, where since the thermal density matrix involves imaginary time evolution by amount beta, you can prepare an Euclidean path integral, and then you can cut the Euclidean path integral at a time symmetric point to prepare this thermophile double state. So if you take any field theory and you construct the Euclidean path integral and slice it in half, the path integral is a inner product between the bra and the ket gives you the Hartle-Hawking or thermophile double state. Now, this construction, of course, works in any system, but if the system happens to be gravitational, something much nicer happens. This construction, if you take that Hartle-Hawking state and evolve it, you will get the future half of the Penrose diagram of an eternal black hole, or if you just look at Lorentzian time picture, you'll get the eternal black hole as the thermophile as the construction in gravity of the thermophile double state. And this statement, of course, inspires various statements like ER equals EPR, because the entanglement that's inherent between the two copies that I've used to construct the thermophile double state, now these Hilbert spaces live as field theory Hilbert spaces into asymptotic region, and they are entangled, and the entanglement is captured by some structure in the geometry. We know that entanglement structure is captured by something, and in the context of Einstein-Hilbert theory, it's simply captured by the area of this surface, which is sitting in the middle, and this surface is a fixed point on the Euclidean time translation isometry. Yeah. So one can just say, okay, fine, it's in a particular theory, it's an area, but it's helpful, and this is what was done by Bob Wall, to ask the general question, suppose I had a diffeomorphism invariant theory which had black holes. What would be the object that computes entropy? What would be the object that supersedes the area functional? What geometric functional should I use? And he showed that actually the functional that you want can be obtained very simply by a Noether procedure. So I won't go through the argument in detail, the equations are just there for amusement, but the rough argument is basically you look at the variation of the Lagrangian, and the variation of the Lagrangian is equation of motion plus some total derivative term. Now you can take the total derivative term and you can do a Legendre transform along some diffeomorphism to construct some current, which is conserved by virtue of equation of motion. It's conserved up to on putting the system on shell, which in turn implies that its conservation implies that it itself is a derivative of some lower dimensional object. So I'm working in this context where everything is a differential form, so my Lagrangian is a top form in space-time. So this charge Q is a d-2 form, and you can naturally integrate this d-2 form on a codimension 2 surface on space-time. And Wald's analysis basically turns this equation into a statement about the first law of thermodynamics, basically dm equals TdS, identifying S with the integral of this Noether constructed charge on the bifurcation surface of the horizon. Yeah? Now, it's important to ask what diffeomorphism is one implementing to construct this Noether charge. Because the Noether charge is a function of the diffeomorphism, it's only a particular diffeomorphism that gives you entropy. Usually, since the construction is done in Lorentzian space-time, the diffeomorphism is one that translates you up along the horizon. Because that's the killing field, that's the static killing, that's the stationary killing field of a stationary black hole. And so you want to sort of use that as a killing field. But it's much nicer to think of this killing field in the Euclidean picture. And in the Euclidean picture, this killing field analytically continues to this rotation around this fixed point of the isometry. And if you view it that way, the Noether charge that captures entropy is really rotations along the thermal circle, and therefore it follows immediately as a corollary the thermal diffeomorphisms are responsible for entropy. So I emphasize this, it's one statement that I want you to take away from the talk, that real-time translations have a conserved charge. This is Hamiltonian. Euclidean time diffeomorphisms, pardon me, not translations, when Euclidean time is compact, give you a charge, and that charge is not energy, it's the free energy current, as I'll show you. Okay, and therefore it's literally, directly gives you entropy. So let me now wants to make a couple of observations. Given that this statement is true for black holes, in fact, the statement is true for black holes in any theory of gravity, not just in asymptotically ADS spacetimes, but at least in asymptotically ADS spacetimes, where black holes map to states, thermal states of a field theory, it must be true as a corollary that we should be able to interpret field theory entropy in equilibrium as a Noether current. Yeah. Correct.
So if like this means we don't apply the equation motion, then the entropy will change. I didn't get this thing.
Well, this means entropy shape that I constructed it can be written as a differential of a lower dimensional form, or only upon using equations of motion. Okay. So it's if you look at the conservation law that I wrote here, it's mostly true, but there's a piece involving the equation of motion. So we should have asked this question a long time ago. How is it that field theory entropy could be interpreted given a Noether interpretation? Let me generalize that statement. I also intentionally wrote down the thermal state as a thermofield double state in a double copy interpretation, because the same set of statements that I'm saying here apply to entanglement entropy, at least in a limited context. If you look at special class of reduced density matrices in conformal field theories, the entanglement entropy is also the entropy associated with some horizon. If you look at, for example, spherical domains in the vacuum sphere for CFT. And in those contexts, again, entanglement entropy, it follows from the logic I just mentioned, is Noetherian. You can ask the question, should that extend to other domains in equilibrium? Should that extend to other domains out of equilibrium? I don't know the answer, but I think that's something that I'm happy to speculate should be true. Another example that has been of interest in recent years is that the ground state entropy of the SYK model also has a relic of this Noether symmetry. In that case, the symmetry is much bigger. It's an SL2, but it's interesting to speculate whether there's a U1 part of the SL, whether only the circle diffeomorphism part of the SL2 is relevant for entropy, or is there a much more general story? That would be right, yes. So in some sense, the modular Hamiltonian is gives you a state, a thermofield double-like construction for any density matrix that you've written down. So if I naively apply the rules, and I know how to deal with modular Hamiltonians, what I'm saying is almost tautologically true. Correct. I mean, in some sense, many discussions involving building Einstein's equations from gravity, etc., while they're restricted to this limited context, they do use exactly this. Sorry, magic. Okay, so that's all I'm going to say about entropy and Noether construction. So let me change gears for a while and tell you about some facts in hydrodynamics. I want to use this partly because this inspired much of what I'm going to say, although I think that the real interesting set of questions lie in the generalizations. But I'll try to convince you there's a story in the context of hydrodynamics that we can understand, and then we can raise the question, we can come back to these questions. So let me answer the first question I posed. If black hole entropy was Noetherian in stationary situations, how is it that field theory entropy in stationary equilibrium is not Noetherian? Okay? Or shouldn't it be Noetherian? The answer is, of course, yes. So I'll prove that to you. It's easy. So we already went through how eternal black holes describe thermal Gibbs states. The easy way to go about this argument involves doing the following. So now I'm going to switch off gravity. I'm not going to talk about gravity for the rest of the talk. I'm going to take some field theory, and I'm going to build a thermal equilibrated state. But to be sort of general, I'm not going to build a thermal equilibrated state that's homogeneously in thermal equilibrium with constant temperature everywhere. I'm going to allow my temperature to vary from space to space, and in fact, the direction of local inertial frame which the temperature is measured, also to change from spatial point to spatial point. The nice way to think about this is basically tantamount to saying that thermal equilibrium will be attained for any field theory by putting the field theory on a spatial background with a time-like killing field. And since there's a time-like killing field, you can analytically continue this time-like killing field, and you can talk about the Euclidean problem, which makes sense. We are talking about equilibrium, and in the Euclidean problem, you can think of the geometry on which the field theory lives as a Klein fibration of a thermal circle over some spatial base. Okay, I'm going to call this geometry M beta. Okay, now the reason I want to do this is now I can do statistical field theory on this spacetime Euclidean spacetime, and I can easily write down the generating function for correlation functions in equilibrium, the real equal time correlation functions of conserved currents, simply by writing down the generalization of the partition function. Now, rather than writing down a partition function, since I'm working with a theory where the temperatures and maybe other parameters are varying from spatial point to spatial point, remember we're in equilibrium, so there's no temporal variation. All I have to do is make sure that I build not a partition function, but a partition functional, which is a function of this background data. Now, this is easy to state. You just do the path integral of the field theory on this background and compute this object. It's harder to implement if your field theory is strongly coupled. In perturbation theory, we can go ahead and do this. But there's a context in which you can actually guess what the structure could be. And that context is when this Riemannian space has variations that are slow in all of the spatial directions. Okay, so all the gradients, which are only spatial gradients, if I allow them to be slow in appropriate units, in units of the local thermal circle, then I can do a derivative expansion for the statistical field theory. And this derivative expansion will give me a partition functional that I can control in terms of data that I can go ahead and compute. The leading order term would just be the homogeneous term, the pressure term of the theory. The next higher order terms will involve thermal gradients, or the vorticity or the field strength of this fibration over this base, or curvatures of the base manifold, etc., etc. And this is exactly what these folks did about 6 years ago. Now, there's a way to interpret that statement, which I just made, that you can write down the partition functional in a context, in a language that's more familiar from hydrodynamics. Basically, you can think of the quantum field theory as irrelevant at this point and replace the quantum field theory by an effective fluid. And you can think of that fluid as being in local equilibrium, which means that you have solved the fluid equations by simply aligning the fluid velocity and temperature to what the background is doing for you. Okay? In fact, the solution to hydrodynamics equations is simply aligning this vector, which is the unnormalized fluid velocity, which I'm calling the thermal vector. It's the local velocity which gives you the choice of inertial frame divided by the size, multiplied by the size of the thermal circle locally. If you align this vector to the killing field of your background, even though you're not in equilibrium, there can be configurations that don't generate entropy for systems when they are taken out of equilibrium. However, if you actually take the system genuinely out of equilibrium, and your system happens to, as most systems are, happens to have dissipation, then there will be actual entropy production. And in the black hole context, this is very obvious. You're dumping stuff into the black hole, the area will grow, or whatever functional will grow. And what you will find is that there's some entropy current whose divergence is given in terms of, at least if you're in hydrodynamics, given in terms of hydrodynamic data. Yeah. So the thing we are most familiar with in gravity are pieces of quasi-normal modes or response functions that lead to entropy production, like viscosity. Now, it's true that most hydrodynamic systems, once you take them away from equilibrium, we go beyond the ideal fluid limit, the first piece you encounter is some viscous correction, so it produces entropy. But if you go to higher orders, there are objects, as I'll mention now, there are transport data which do not produce entropy despite not being visible in equilibrium. So an example is a second order transport like the shear squared term. So you can write, if you just look at the energy momentum tensor, second two derivative order, instead of writing shear viscosity times shear tensor, there's another tensor structure, two derivative order, which is some new coefficient times shear tensor made into a two tensor. That guy, that coefficient, or appropriately combined with other things, that guy does not produce entropy to all orders in the flow. So it means that there are quasi-normal modes, or linear combinations of quasi-normal modes, or pieces of quasi-normal modes that have no imaginary part, effectively.
So one can use that to actually construct configurations of black hole or excitations about black holes which do not generate entropy.
I think not, because all of these configurations, if you're not in equilibrium, it's easy, and because but the moment you turn on things which are interesting, which involve shear, the viscosity term will kick in, because that's always the leading order effect. So there's subleading pieces that don't produce entropy, but I think the leading order piece always produces the entropy. So you have to be careful about this. So I don't think it's possible to engineer a configuration where the black hole is genuinely out of equilibrium, but not
what one would.
Yeah. Okay. So so let's try to capture this information in some data, and rather than tell you how it's done, I'll just quote a theorem for you that was proven 4 years ago by Shantanu Bhattacharya. And this theorem is going to be helpful because it's going to help me organize the data in what follows. What she showed was the following. She showed that it's always possible to construct a current, which is in hydrodynamics, so at least in order by order in derivative, which satisfies positivity of entropy production. The divergence of this entropy current is positive, non-negative definite, provided the leading order pieces, like viscosities in this case, have definite signs that system has friction, doesn't have anti-friction, and you can get hydrostatic data from the statistical field theory I just described from this partition function. You can take her theorem and basically go back to this intuition of constructing this Noether current and build a more general object. You can sort of look at the difference between the divergence of the free energy current and this combination of energy momentum tensor and the lead drag of the metric background. The metric is, I remind you, we are not doing gravity. Metric is just some background source which allows me to pull out energy momentum tensor. I can build this gadget, and in equilibrium, I showed you this was 0. I also argued for you that configurations or situations where this would be 0, even if you're not in equilibrium, but generically, it will be, if it satisfies second law, it will be something positive. And you can classify, you can sort of take this equation as a functional equation on the space of energy momentum tensors and free energy currents parameterized by this vector beta, which is the hydrodynamic data, and the background geometry data, which is the metric. And you can basically use this to build solutions of this functional equation. There's a class of solutions which is not interesting, but whose classification is not that interesting for what follows. But what is interesting is that you can isolate, using Shantanu's theorem, you can isolate the piece that corresponds to dissipation, and this is what's going to be important later. And the trick is the fact that there is this one lead derivative of the metric with respect to some background vector field which measures fluid flow. So you can use that as a counting parameter, even though you're doing derivative expansion. And you can show that by cleverly organizing things, all entropy produced can be expressed as this following 4 tensor, which has symmetry properties as written, plus symmetry properties in exchanging the first 2 indices with the second 2 indices, times 2 lead derivations on the metric. Okay? Provided this 4 tensor is a positive definite inner product on the space of two tensors. In fact, generically, since I'm hiding lots of details, this guy is a derivative valued operator. It's not just a tensor, it's a tensor valued operator. Provided that tensor valued operator has positive eigenvalues, etc., it follows that entropy is always produced. So her theorem basically guarantees that you can do this, and this is a sort of summary of this theorem. Now, yeah.
The theorem says that if I take the equilibrium partition function and the first order like viscosity conductivity,
yeah,
there is no more dissipative coefficients, right?
As long as everything else is obtained by hydrostatics.
Yeah, and then what do you mean by the last line? Then what are the terms you are constructing here?
So there might be higher dissipation terms. I didn't say that there's no dissipation. They're just not constrained. So if you have a dissipation at 15th order, its sign is not determined. It doesn't have to be of a definite sign, unlike viscosity.
I see. So they can even entropy might be reduced.
No, entropy is always produced with the right entropy. Divergence is always positive, irrespective of the sign of your 15th order dissipative coefficient.
I see.
Because, I mean, roughly speaking, because it's 15th order, it's always dominated by the leading order piece. Okay. So you can think, since I told you can think of this functional equation. So remember this equation, this piece, that amount of entropy produced is measured by two Lie derivations on metric. And remember this equation, which are the only two things I want you to remember. Okay. Now, let me take a moment to pause and complain a bit about black holes. Now, the reason to complain about black holes is that in hydrostatics, this seems like a very clean logic. You just go through this logic and you construct this object. But if you think about it for a while, the entropy current is a very unnatural object in field theory. You build it in hydrodynamics, but if you look at it in the ADS-CFT context, this guy is associated with horizons. It's not associated with conserved currents on the boundary. All conserved currents, like energy momentum tensor, they are obtained by some, if you like, Pfefferman-Graham-like expansion by living near the boundary. But the entropy current is some feature associated with horizons, as various of us pointed out in the context of fluid gravity. And you may wonder whether similar statements hold away from equilibrium, and whether you can say statements of this kind about entropy when you're not just in hydrodynamic limit, where we understand how to build the field theory entropy current using black holes and their horizons, but for more general horizons. So what is the set of statements we would associate with entropies in general? We don't know this, but this is another set of questions I want to put forth in the context, thinking more generally beyond what we've done, because there are many possible coarse grainings that you can do to any given system. And there should always be some associated monotonicity property with those coarse grainings. What do those coarse grainings mean, and how do we interpret them both gravitationally and in field theory? I don't know a good answer to that question. One thing I will say, which I find intriguing, is it's also not. We also so far do not have an analog of second law for general theories of gravity or arbitrary variations away from equilibrium. So Aaron Wall, about 4 years ago, proved a theorem which says if you have stationary equilibrium and look at the Wald entropy, or actually its correction, which includes entropy coming from entanglement that Zhidong found, that quantity satisfies second law to linear order in amplitudes, in the small amplitude expansion. There is no statement, unlike the area theorem, that there is a second law for black holes in general for any higher curvature theory of gravity. An attempt to do such a construction, which some of us did, gave us a structure that's very similar in spirit to this construction. There's some caveat, which is why we can't claim we have a theorem. So ask me later. But so that there is some close connection between how entropies are produced and this equation. And you'll see a relic of this equation later, which is why I bring this up as an interesting equation to understand from a gravitational point. Right now, this is just an equation that is inspired by hydrodynamic analysis, and I'll show you how to both derive it and understand it in general. Okay. So I also told you that we had, apart from dissipation, we had lots of solutions to this functional equation which didn't produce entropy. In particular, the solution I was mentioning, the example I was mentioning to Rajesh. So there are many other things, the anomalies, there's Hall transport, all of which are not equilibrium data, but they don't produce entropy. And our attempts to understand this led us to two statements, which I'm going to use to inspire myself to what I say for the next part of the talk. One is you can understand them by working with not one, but two sets of degrees of freedom with some appropriate constraints. And this equation that we cooked up must hold as an official statement, as a Bianchi identity on configurations in that system. Okay? And it must also be true as a corollary that the free energy current must be a Noether current for thermal diffeomorphisms. So in what follows, I'm going to explain these statements. These statements are true. And then that will sort of get to my second bullet point in my synopsis. And then I'll show you how the third bullet point comes up. So to do that, I'll pause. I'll provide you with some insight into how we should go back, forget about hydrodynamics for a while, and go back and think of coarse graining by starting in some Gibbs state of a quantum field theory. We should start with some Gibbs state that's prepared for the microscopic degrees of freedom, integrate out all the high energy stuff, write down the low energy state, and ask how does hydrodynamics emerge? Couple of things must be true if this statement was to be correct. That the dynamics of low energy modes must be universal. It shouldn't care about what theory I started with. Hydrodynamics is built out of very small pieces of data. It's built out of velocities and temperature. It doesn't care about whether I put in quarks or gluons in my underlying microscopic theory. A second statement, which I'm going to emphasize as would be necessary, is that dissipation and associated CPT symmetry breaking should arise from some dynamical principle. You shouldn't put it in by hand. It's basically related to the last statement, that if you're trying to do real-time dynamics in a mixed state, you need rules, as I'll explain. I won't explain in great detail. You need rules to tell you what low energy interaction terms are allowed. A generic low energy interaction term that you can write down following your nose in a Wilsonian procedure will not respect microscopic constraints. So I'll have to tell you what the microscopic constraints are, and then we'll see why this is. Okay. There's one more requirement that's actually important, that the macroscopic theory shouldn't just be classical. In addition to telling you what the classical hydrodynamic theory is, it should also, by virtue of it arising from some microscopic structure, tell you how fluctuations take you away from that guy.
If you just took a very highly excited energy eigenstate, you would expect exactly the same kind of low energy dynamics, right?
Well, if you're suitably coarse graining, I agree with you. Yes.
But I mean, right. So you look at low energy, field theory dynamics at distances which are not very short, and you should see the same formula.
I agree. Yeah. I mean, but that's secretly because I am going to assume ETH because I'm going to work in a Gibbs state. So if you're happy to do that, then it would just be true.
Then of course it's true.
Yeah. Okay. So given this interlude, let me take an interlude and tell you a little bit about the answers to this question about what constraints we should impose. I unfortunately won't go into any great detail, but we'll tell you the following set of statements. So first, let me just remind you what we do in hydrodynamics. What is it that we measure? What we capture when we say we're looking at hydrodynamic transport is the following. You take your Gibbs state, it's prepared in equilibrium, and then you come and you disturb it. You disturb it again. Disturb it again. And eventually, after a series of disturbances, you make one measurement. Okay? And that's a response function, because you take this, you drive the system away from equilibrium, and then ask how does the system respond to your having driven the system away from measurement. The natural language or natural quantum field theory framework for doing this is computing what in modern parlance would be called one out-of-time order correlator or a Schwinger-Keldysh correlator, where you build two copies of a theory, which is again intuitive from this thermofield construction that we talked about, and the disturbances that I'm making are concerted disturbances where on both copies I do the same thing, whereas the measurement breaks the symmetry between the two copies. Now, the reason you have to make one measurement is that if all you did was disturbances, and if you did only concerted disturbances of your system, then you're doing nothing, because this path integral contour evolves forwards in time and then evolves backwards in time. And if you were doing the same thing on both legs at the same instances, then this is basically just inserting a resolution of the identity in some funny basis. So that measurement breaks the symmetry, and these response functions are what we want to measure. So in some sense, these response functions are the first non-trivial thing that exist in Schwinger-Keldysh effect in the Schwinger-Keldysh computation, because without this measurement, there is no correlation, nothing to measure. It's just everything you would measure is zero. So it therefore follows, at least intuitively, that there must be some underlying structure, the first deformation to which must be hydrodynamic response. The statement I made about fluctuations is related to the following, that because my state is a give state, and this end line here represents the fact that you do your evolution in real time, go back, and then you evolve back in imaginary time for your density matrix by an amount beta, it tells you that the theory must satisfy what's usually called the Kubo-Martin-Schwinger KMS relation, which is a statement about, if you want to be formal about it, it's a statement about analyticity of the correlator in the half strip. But it really is a statement that this particular time-ordered correlator is related to the opposite time ordering, because the density operator, which I'm computing, there's a row missing here. This density operator is e to the minus beta h. Taking suitable combinations and going to Fourier space, you'll get back your usual fluctuation dissipation theorem, from which the Einstein relation follows. But upshot of this discussion is simply that associated with this response, there's a class of fluctuations that your effective field theory has to get right. Because these fluctuations are not arbitrary, they're purely dictated by this relation. So it will take me too long to explain what our philosophy was to build this. There are three statements. So we need this doubling, so we'll have work with two sets of degrees of freedom. Two, we'll need some way to encode this unitarity. So we are going to do that by realizing that when things are aligned, nothing happens. So we're going to use intuition from topological field theories to say that there's some underlying BRST structure. And third, to say these KMS relations, I'm just going to say, well, this looks like periodicity in imaginary time. So on top of this BRST structure, I'm going to impose some symmetry that keeps track of this KMS relation. I'll give you a heuristic, and then I'll write some formulas. The heuristic is roughly this. Think of your non-equilibrium quantum field theory as now a circle fibration over a Lorentzian spacetime. So previously, I had a circle fibration over a Euclidean base, and that was statistical field theory for equilibrium. Now I'm going to think of circle fibration over Lorentzian spacetime. This is too much data, so I'm going to quotient out in some sense by demanding that in some heuristic sense that the sort of sections of the fibration don't matter by imposing an effective gauge invariance. The gauge invariance I'm going to impose is one where circle diffeomorphisms are gauged, and they act on fields by this. The symmetry group I want is given by taking two objects that transform in the adjoint of this symmetry and writing on a bracket which involves this beta vector that I introduced before. So, sort of distilling all those statements, this macroscopic theory will have two sets of fields. The real fields that I'm measuring, the average fields are the things that will appear in hydrodynamics. They're associated fluctuation fields.
Just one question.
Yeah.
What is the
There's also a fifth Euclidean circle, 4 plus 1, 3 plus 1 plus 1. Or because time has a cylinder that's fibered over free space. I'm going to add to this some BRST structure. So everything I'm going to say is going to be written, equations are going to be written in employing this BRST structure covariantly by writing instead of equations in position space in space-time, I'm going to write them in super space-time. So I'm basically going to take my space and append to it two Grassmann coordinates that allow me to simply talk about this BRST structure. And the intuition is that this BRST symmetry and this thermal gauge symmetry, they encode and capture consistently all the data I was just telling you about. They capture the features that I wanted, microscopic unitarity, and the KMS relations. The algebra that, if you're interested, looks something like this. So basically, I have two supercharges, Q and Q bar. They are not, since I'm working in some gauge covariant language, they are not nilpotent, but they sort of transform. They're nilpotent up to gauge transformations, and the gauge transformation is a thermal diffeomorphism. So it's basically this L beta, which I've written as LKMS here. I'll also say that this algebra is well known in some circles, and it was also rediscovered by our friend from MIT. If you take this algebra and you gauge fix these field strengths or gauge fix the background potential, then in a particular gauge, this algebra looks like you have two nilpotent charges, which anti-commute to give you an Hamiltonian, which is thermal diffeomorphisms, which is nice because then I can talk about entropy. And it's logical to guess that this actually, and this statement actually, I should say, is strictly speaking true in the high temperature limit. It's logical to speculate that the actual completion away from the high temperature limit involves this this statistical factor, but I won't talk about going up on the high temperature limit. The high temperature limit is essentially like h bar going to 0 limit. It's a classical stochastic limit of this problem. So I'm going to keep track of thermal fluctuations. I'm not going to be in position to keep track of quantum fluctuations. So just to tell you where this structure has been seen a long time ago, this is, you can think of the simpler problem of thinking of Brownian motion in this language. And if you take all the statements I said, without any of the details that I didn't give you, once you supply them back, you can write down an action for a Brownian particle involving two sets of variables, the position variable of the particle, the physical position variable, and a stochastic variable that keeps track of how the particle is fluctuating about its mean trajectory. And covariantly implementing this BRST symmetry tells me that I need to put in these ghost fields. I'm agnostic at this point whether I actually need the ghost fields or not. So ask me why that's the case. And this effective action, if you appropriately use this kind of gauge fixing that I mentioned here, precisely reduces the actions that you will see which are described in literature going back 4 or 5 decades. But it has one nice feature, which none of these actions have. This action has a mechanism to dynamically break CPT and generate both a dissipative sector and an anti-dissipative sector. In the following sense, as long as this gauge field, which in this case is a one-dimensional gauge field, so it doesn't have any real data, is dynamical, I can have a dynamical principle that picks out a choice of dissipative vacuum or a choice of anti-dissipative vacuum. So in this formalism, with a thermal gauge symmetry, CPT symmetry breaking becomes a question of dynamics. I will also admit that we do not understand fully how this topological gauge dynamics of this thermal gauge field works. Okay? There are interesting conjectures we can make about how it should pick out the right vacuum, but whatever vacuum it picks, as long as there exists a vacuum with this choice for the field strength, it follows that it will at least capture the physical dissipative sector of interest. Okay. Questions about this? So there are different sectors. So one sector, when you gauge fix, will give you dissipation. But if I fix, for example, if I fix this f theta theta bar to minus I, instead of minus I to plus I, I'll get anti-dissipation.
So it depends on.
It's a Z2 symmetry breaking, so it's really that, because it's a symmetry breaking for a discrete symmetry. Rajesh. So I had a gauge field.
It's like a field strength.
It's a field strength of a gauge field. So I had this thermal gauge symmetry, but it was upgraded to superspace. So in superspace, my gauge field is really a super form, and there's only one object in that gauge multiplet which has the right ghost number to pick up a wave. Okay? And it's just this. So the system is not unconstrained. It's reasonably constrained. So the speculation is that there is a simple BF theory you can write down for this gauge dynamics that will pick out this vacuum. I don't want. So I think that's true. We just haven't done it. Okay. So finally, in last order, I'll tell you how to write down hydrodynamic theories. It's very straightforward now that you've seen a Brownian particle. You don't have to work too hard. The easiest way to say this is just think of fluids as space-filling brains in this topological sigma models, in this topological context. So I have a physical fluid that lives in some space-time. It has some local velocity and local temperature encoded in this vector beta. X mu is the coordinates of this physical space-time. You should view X mu just as you view D-brane dynamics in physical space-time in terms of some world volume data, where on the world volume, I have a pullback metric, a pullback. I can, instead of thinking about beta, I'm going to fix some reference flag to tell me what my inertial frame is on the world volume, so that the push forward of this reference flag to the target spacetime will give me the physical velocities. Okay, this is a clever way, if you like, of doing the following. Beta is a dynamical variable, but strictly speaking, not all of beta is physical, because part of beta sort of picks out an inertial frame, and you want to be in equilibrium with respect to an inertial frame. So wouldn't life be simpler if you sort of homogenized your equilibrium, which you can't do in physical spacetime because temperature is varying from place to place, but you can on this reference manifold. So you can bury all the non-trivial spatio-temporal variation of beta into this map. Okay? And in addition, for all the symmetries and BRST structure that I wanted, I have this gauge field that lives on this brane. This target space map has a physical spacetime coordinates and their fluctuation partners and potentially ghost partners. And what I'm going to do is write down a topological field theory, which will capture the sort of boring sector and argue that just by slowly deforming away from the topological sector, I can write down the hydrodynamic theory. After all, that was true for response functions, so it must be true for the effective field theory. One more statement. Encoding the dynamics in this push-forward map from the world volume target space is nice, because it makes clear why the equations of motion of hydrodynamics are conservation equations. Any classical Lagrangian you write down, equations of Euler-Lagrange equations are not equivalent to energy momentum conservation equations. There are Noether constructs from diffeomorphisms. So the only way you will get a dynamical system with conservation equations as dynamical equations of motion is if your fields, if in field space you have diffeomorphisms. That's what's happening here. My chairman is telling me I'm running out of time, so can I take 3 minutes? Okay, so actions are easy to write down. I won't go through them in any detail. And there are rules for what actions are allowed. The rules are sufficiently constrained that you can't do random things. The nice thing about this is that once you establish the rules, actions are just easy to just write down once and for all. So here's some example. Basically, the first piece is an ideal fluid But now instead of writing an ideal fluid as a partition function of the pressure function, you just take the pressure function and take it off shell and write it as a pressure function in the superspace. Similarly, you can write down viscosity terms. And you can also argue that entropy production follows from similar arguments that I gave you before. Okay, so now I finally have 3 minutes, or whatever remains of 3 minutes, to tell you how entropy gets produced by inflow. Now, it's actually very simple, so I don't need much more time than that. So here's my Lagrangian, which has a lot of symmetry. So all I'm going to do to this Lagrangian is implement this thermal symmetry transformation. Okay? I didn't write down the gauge dynamics, but I can do a gauge transformation and ask what Bianchi identity I get. So Bianchi identity I get is this. Okay? And this is why I just emphasize, I didn't say this before, these I indices are both physical indices and superspace indices. And the reason I told you to remember the adiabaticity equation is that this should be now familiar. The super divergence of super entropic free energy current plus some combination involving the super free energy momentum tensor is 0. It's the same combination if I set all these indices to physical indices, which would give me the adiabaticity equation with no entropy production. Let me decompose this equation into physical and super directions. Trivial rewrite. And I look at the right-hand side and I examine it. I find that the right-hand side precisely has the right structure to be interpreted as entropy production. In other words, this equation, which is homogeneous in superspace, if projected down to physical space-time, becomes inhomogeneous, and the inhomogeneous part, which corresponds to entropy production, is precisely the the superspace divergence of the supercomponents of the energy moment of the free energy current. And this is what inspires the statement that entropy is flowing in from superspace to be produced, to actually be seen as being produced in physical spacetime. There's an obvious question that some of you might have. If everything has super directions, why is energy momentum conserved? Empirically, it turns out that the correct energy momentum tensor equations work, even though the actual conservation equations you would derive are the super conservation equations. I must confess that we know this. So in the previous case, I know a logical scheme of arguments which will tell me why this is true. In this case, we know empirically that this works. I don't have an intuitive reason to say why energy momentum also does not flow in from the superspace to physical spacetime. There's some statement about Jarzynski, which I'm not going to tell you. Okay, so 3 statements I made, some of which I sort of breezed through at the very end, are these 3 statements, that there is something Noetherian about entropy, both in equilibrium and out of equilibrium, at least in hydrodynamics. And I emphasize that this Bianchi identity is Noetherian, because it comes from variation of some background field. So this, I think, is a powerful statement and begs for various questions, some of which I'll just flash. What kind of lessons do this mean for gravity? So we know that equilibrium entropy in gravity is Noetherian. What about non-equilibrium entropy? Should non-equilibrium entropy also be interpreted this way? You can rightly complain to me that none of the structures that I've put forth here, all these BRSC structures and these superspace directions, seem to have any analog in gravity, but I will reverse the argument and say, just as we started at the beginning and said, since world construction tells you entropy is Noetherian, there must be a statement of the corresponding kind in field theory. Now if I just take this statement in converse and say, for field theories in certain configurations, I know that entropy is obtained from a Noether procedure for some enhanced symmetry. Shouldn't this enhanced symmetry be there in the dual gravitational sector? Okay, I think I will stop and pause to take questions. Well, let me just flash, if people are interested, this is all the sequence of papers that I actually bother mentioning in detail, but there's some papers that we've written and some papers that others have written that you can find. Okay.
Mukund, I think I heard you say the word Jarzynski.
Yes, I did.
Would you please elaborate how your formalism might throw light on?
So actually, the relation is much older. Since I have a symmetry, I can convolve this. I can convolve the symmetry transformation, this thermal symmetry transformation, with a CPT transformation, and ask how does the action transform. Okay. So the argument is due to these folks in the context of Langevin, but I think the same argument goes through in hydrodynamics. If you look at the action transformed under the symmetries with all the structure, you find that the transformation, the action is not invariant, but picks up an inhomogeneous piece, which is precisely the Jarzynski combination. Okay? Since the symmetry is the symmetry of the action, must be true that Jarzynski is true. So it's roughly speaking an about identity for the BRST symmetry.
Thanks. In the conservation of the energy momentum tensor, when you said you know it empirically, you mean you know it in
various examples.
Cases, but can one not show that the right-hand side, does this F theta theta bar appear on the right-hand side there or not?
Okay. Yes, it does, but it's not good enough. That's partly the problem. The problem is this. See here, this equation is useful. So here, this guy, T theta theta bar, is also ghost number 0. Okay, so it can be, so anything that has ghost number, you can just forget about that. That's easy. That's an easy argument. But for example, these combinations, they don't have. I mean, this is physical because it has ghost number 0, which means it can depend on the physical fields and the fluctuations. Okay, because those are the only ghost number 0 fields in my game. In this case, it's easy to argue that this guy has a right contribution from the physical fields to be interpreted as entropy production. If you look at the expression for T theta theta bar, it also has contributions from physical fields and fluctuations. If it only had contribution from fluctuations, life would have been perfect. You could have just said, well, in classical hydrodynamics, you do not see these super components of energy momentum tensor. But it does have contributions. What happens in the conservation equations is very similar. You have derivatives, super derivatives on these guys, which are not Grassmann even to begin with, but they conspire to cancel with T theta theta bar. So that's why I meant empirically, it's something we know in wide variety of examples, but I don't feel that we have an understanding to tell you that there's a principle that forbids energy momentum from flowing from superspace.
This is about your last comment about relation to gravity.
Yeah.
So is this degree of your degree of freedom also superspace is maybe localized as an edge mode in gravity, or what do you have any speculation about how it appears in gravity side?
Yeah. So let me speculate. So imagine you're actually computing real-time response functions in gravity. So again, in gravity, you do some Schwinger-Keldysh construction, and there I would tell you that the way to encode the effective field theory construction is to put in the superspace. So in addition to the gravitational degrees of freedom, maybe I have 2 copies of gravitational degrees of freedom, but I'd also have this gauge field that consistently couples them to keep track of what's happening. Okay. Now, what's confusing about this is that in field theory, the thermal behavior is something that you put in by hand. It's some boundary condition. You just decide to take the field theory in a thermal background. In gravity, things start getting confusing with the fact that there's a dichotomy between wanting to put in thermal backgrounds as some boundary condition, like for example, the size of the circle at infinity, with the fact that dynamics also tells you what this thermal circle does. Okay, so this is why I don't feel 100% sure how to actually implement this, but that's a rough intuition.
If there are no further questions, let's thank Mukund again.